Absolute zero. To investigate how the volume of a gas changes as its temperature changes at a constant pressure, we can use apparatus something like this. We have a narrow glass tube sealed at the bottom with a short length of concentrated sulfuric acid somewhere along the tube's length. We can measure this distance L, which will give an indication of the volume of the gas, as the tube is parallel. The sulfuric acid simply removes any moisture from the air, giving more accurate results. We can then place this in a water bath, using a thermometer to record the temperature, and also recording the length and therefore the volume of the fixed mass of air in here. The tube is open to the top, and so the pressure will always be atmospheric pressure. We can then plot a graph of how the length of the column of air, and therefore the volume of the column of air, is changed as temperature in degrees C is changed. We'd get a line something like this. If we now extrapolate back below 0 degrees C, the line would come down to here at minus 273.15 degrees C. This is showing at what temperature the length would be 0, and therefore the gas is taking up 0 volume. With this apparatus, we can find out how the pressure of a fixed mass of gas is affected by temperature, now at a fixed volume. The volume will hardly change as the pressure of the gas increases. Now, plotting a graph of the pressure against the temperature in degrees C, we would get a line again something like this, and again extrapolating below 0 degrees C gives 0 pressure at minus 273.15 degrees C. We know from the video on the kinetic energy of gas molecules that the total internal energy U of n molecules of an ideal gas at absolute temperature T is given by U is equal to 3 over 2 nKT, where K is the Boltzmann constant. If there is 0 temperature, the gas has no internal energy. As the internal energy of an ideal gas is all translational kinetic energy, this means the molecules will stop moving. Therefore there will be no collisions with the sides of the container, and so no pressure. Also, as the molecules themselves have negligible volume, the gas will have 0 volume. The temperature at which we get 0 pressure and 0 volume for a gas is called absolute zero. You cannot get a lower temperature, as the molecules cannot have less than 0 kinetic energy. Quantum mechanics, however, tells us that there will always be some kinetic energy, so absolute zero is the temperature at which the molecules have a minimum of energy. We generally cool objects by placing them in thermal contact with an object of a lower temperature. Clearly we cannot do this to reach absolute zero, so other methods are used. Scientists have managed to cool down to just 0.5 billionth of a degree above absolute zero. So absolute zero occurs at minus 273.15 degrees C, which is known as 0 Kelvin, given the symbol capital K. To convert Celsius to Kelvin, we must add 273.15. So, for instance, 50 degrees C is 323.15 Kelvin. A change in temperature is the same in Celsius or in Kelvin, because the increment of 1 Kelvin has been made to coincide with an increment of 1 degree Celsius. So if we were told a temperature goes from 50 degrees C to 80 degrees C, the change in temperature is 30 degrees C, or equally, it is a change of 30 Kelvin. In the experiments described in this video, any units of volume and pressure could have been used, and we would have got the same results. As no litres is the same as no cubic meters, or no gallons, or no millilitres, etc. Any volume measurement has 0 when there is 0 volume. Equally, 0 pascals is equal to 0 pounds per square inch, or 0 bar, or 0 atmosphere. All pressure scales have 0 at 0 pressure. But when we're using temperature, we must use the absolute temperature scale, because 0 degrees C is not equal to 0 Fahrenheit, which is not equal to 0 Kelvin. There is only the absolute temperature scale, the Kelvin scale, which has 0 temperature with a value of 0. However, in all calculations, don't forget to use SI units throughout. If your data is put in SI units, the answer will also come out in SI units.